But there's this big gap between super bright stuff and
Okay, today we're very happy to have Evgenia Shkolnik as our keynote speaker. Evgenia is an expert spectroscopist working at the interface of stars and planets, particularly stellar activity, dynamos, young stars, and the magnetic interactions between planets and their host stars. What she'll talk about today is an interesting new role where she's sort of at the vanguard of a burgeoning field of small-sat astronomy as a PI of the SPARCS CubeSat mission. Evgenia did her undergraduate work at Dalhousie up north in Nova Scotia. She did her PhD at the University of British Columbia. Gordon Campbell, right?
No, Gordon Walker.
Gordon Walker, sorry. Then she did postdocs at Hawaii and Carnegie DTM before she was on the staff at Lowell, and now fairly recently moved to ASU, where she's an associate professor. So she's going to talk about a blast from the past. I see you've changed your title slightly. The evolution of UV emissions and flaring from low-mass stars and implications for habitable zone science.
Okay. Thank you, Sean. All right. Am I on now? Unmuted? Yes. Okay. Well, great. Thank you so much for the invitation. It's great to be here for the second time today. I gave an earlier 10-minute talk on star-planet magnetic interactions, so thank you for mentioning it. I will not get to talk about it here. Okay, now I can't see you. How will I know if you're not anyway, I've had a fabulous couple of days here. It's been so interesting. I have a notebook full of notes of great ideas from postdocs and students that we all talked about and brainstormed about. So it was really fun, and I feel super relaxed because I haven't been on email all day. So that's been really amazing too. And now I'm ready to go back to it. So maybe we can all just keep hanging out. All right, so as Sean said, this is sort of new, probably a few years. I've been working on the UV emission of low-mass stars for a very particular reason, is that it turns out that we don't know much about the UV emission from stars, and it's very important so that we can understand both the stellar activity, but also the planets around all these stars, right? So I'm interested in how the UV affects both the evolution of exoplanetary atmospheres and the potential photochemistry that we need to understand in order to be able to interpret our transmission or emission spectra, or even reflected light spectra eventually of planets, including habitable zone planets. So I have one introductory slide to catch everyone up into the same realm, to keep everyone thinking about exoplanets. So here are 4 facts that I think are relevant to today's talk after 3 decades of planet hunting. So one thing, exoplanets are everywhere. I think everyone here knows that, right? On average, at least every star has at least one planet. They're extremely diverse, more diverse than the exoplanets in our own solar system. There are roughly 12 habitable zone planets now. Known, of course we can all dispute what that means, but we're not going to do that today. But most of those 12 are around low-mass stars, so these M stars. And if you work out the numbers in our own galaxy, and whether it's 25% or 10% or whatever the actual occurrence rate of habitable zone planets are around low-mass stars, but it's something, and it's something that's greater than 1%. So it works out to be about tens of billions, with a B, habitable zone, small planets around M stars in our one galaxy. Right, so when you think about what my goal, my life's goals, in part, are to understand the distribution of planetary, including habitable environments around our galaxy, and I bet for some of you, at least in the room, not all of you, but for some of you, you're also very much interested in this. So I'm also going to talk about M stars in a more specific way than you might be used to. Here is a nice reminder plot, and I plot mass increasing this way to confuse all of you, and make sure you're paying attention, and showing you the FGK stars, and these are the M stars here that span 3 orders of magnitude in luminosity and run from about 0.1 to 0.6 solar masses. But not all M stars are the same, right? And I think that at least I had lunch with Charbonneau's group yesterday, and I know that at least he likes to say that the late M's are the real M's, and the early M's are not real M's. But I'm not going to break with tradition today, so I'm going to keep calling these early M's. And but I am going to distinguish between early, mid, and late M's, because you're going to see charts that show the different UV evolution of all these three kinds of stellar types. Now, if we do have, say, a planet in the habitable zone around a late M, let's say like Proxima b around Proxima Centauri, right? And you want to envision what this really means, and it's about 10 stellar radii from its host star. Take an image of a solar eclipse like I've done here, right? Pretend now it's Proxima Cen, right? So scale everything down, put Proxima b in its position, and it looks like this. Okay, this is, I think I really enjoy this visual because what it means is that Proxima Centauri b is existing in a very different radiation environment than we are here in our comfortable 1 astronomical unit. I put a little magnetic field here. I don't know anything about planet Proxima Cen b's magnetic field, but it was the topic of my earlier talk today. So just keep it in mind that someday it'll be important. But the planetary consequences at these high energy The planetary consequences of the high energy radiation at these close distances are abundant, and here's just a few. One is the atmospheric heating and escape by extreme ultraviolet photons. Another is the effect of the photochemistry, so you can have photodissociation of the molecules you are particularly interested in looking for. So if you're looking for water, but it's been photodissociated by UV, you want to know, right? Has there ever been water there and it's just been photodissociated, or was there actually no water? And of course, if this, both of these might affect the surface habitability of any planet. And lastly, it will affect the detection of the habitable, whether a planet is habitable and or inhabited, right? Because in fact, the UV has pathways, chemical pathways that create both false positives and false negatives of the biosignatures we're currently talking about in our community. So this is problematic, and this is what really set me off, right, into the UV direction at some level, is because I want to live long enough to know that a detectable biosignature is detected and believable. And so I'm now getting concerned with all these other ways that we can do it. So I'd like to contribute to that question. Here is a plot made by one of the postdocs in my group, Dr. Park Lloyd. It's the UV and X-ray, well, here's the UV and X-ray part of an M-dwarf spectrum. It's just an example. And what you see is that here's the black body part of the M-dwarf, right, peaking at around 1 microns. And you see here's the UV component here, right? And there are very few UV photons. He, in fact, had to increase the y-axis by a factor of 100 just to show you the emission features. So there are very few. Like, there's literally 1 million red photons to every UV photon, right? But not every photon is equal, right? So, trip on something here. And so the near UV photons and the far UV photons here can photodissociate the molecules, as I already said. And the high energy ones can lead to ionizing of the atmosphere and then potential stripping of the atmosphere from the stellar wind. All of this can cause trouble with the planet and how we interpret the planet spectrum. So my collaborators at VPL, the Virtual Planet Laboratory, led by Dr. Vicki Meadows at the University of Washington, created these plots for us and for them, but in anticipation of trying to understand this and motivate the reason for more UV observations of M stars, especially those with known planets, especially those with transiting known planets. So here's an example of a transit spectrum of a habitable zone modern Earth around an M3, so it's kind of a mid-M, with variable UV, where you can have the low, so if the exact same planet in the exact same position is orbiting an M3 that has low UV emission, then you can see the black curve is the resultant spectrum. And if you have 10 times the UV emission, and 10 times is not that much, right, in the UV, then you can have the blue spectrum. And so you would interpret the spectrum completely differently. Another example would be here's the reflectance spectrum. Spectra of a modern Earth around an M2, just as an example. And you can see again the methane that you would observe in reflectance spectrum, in the reflectance spectrum of this particular planet, is affected by its central star, not by the content, not by the actual intrinsic methane on the planet. So the wavelengths of interest that I'm talking about here, when I say UV specifically, these are the photodissociation cross-sections of trace molecules you might be interested in looking for, right? So here's the extreme ultraviolet. Now this have large cross-sections, highly energetic photons, really hard to observe for most, well, at the moment you can really only observe the EUV for the sun. There was a mission, EUVE, in the past that observed 6 M stars. We have a fundamental limit in the EUV, that we have the ISM absorbing the EUV. So really, we're never going to have like a large sample of exoplanet hosts in the EUV. So we need to find a way to get to the EUV. And the way that we have been doing it is using the far UV and the near UV, both because the photochemistry depends on the far UV and near UV, and in fact the ratio of the far UV to near UV and the photoevaporation depends on the EUV. And so we're trying to use what we can observe, right? In this case, I'm showing you the Galex band passes. I'll show you them in more detail in a minute. And so we're observing this to understand both the far UV and the near UV and the EUV. Now visually, so as I said, the sun is the only star for which we can now observe the EUV, but another beautiful visual is these SDO images, because what they're really showing you is how the sun, as we traditionally imagine it in the optical, looks very different in the far UV and the EUV and in the soft X-ray. Spectroscopically, this is what a similar idea looks like, right? So here we have a spectrum of an M dwarf, ET Cha, it's a young active M dwarf, and you can see how the photospheric models, these are the Phoenix models that everyone knows and loves and we've been using for a long time, completely underpredicts what is happening in the chromosphere in the transition region by orders of magnitude. And this is not because Phoenix are bad models, right? They're great models and we love them, but they were never designed to predict the chromosphere and the transition region of the corona. So what we want to do is advance the Phoenix models in order to do these upper atmospheric layers as well. So our beautiful sun flaring. So we know, and I'm not going to go into all the evidence of it, but I think that we all know that M dwarfs are more active than our sun. We want to know how active they are in the ultraviolet, and we want to know how active they are across planet formation and evolution timescales, right? So now it becomes not just knowing what the planet is doing now, but also what the star was doing now, but also what the star was doing at the time that the planet first formed, right? So we know that the sun was much more active in its youth. We now know that, and we know that M dwarfs are more active in their youth as well. And so I'm going to show you the evidence of how we got to know the details of what we already kind of knew going into this. So we're doing it in 3 ways. One is we're using, it's what I would consider the past, present, and future of UV evolution of M stars. So we looked at archived data from Galex, which is no longer functioning, but we do have the archive that it's left us. It left us about 2/3 of the sky mapped in NUV and far UV photometry. We have ongoing HST spectroscopy of young low mass stars going on now. And then, once we have kind of exhausted the time domain with HST, we now need a monitoring campaign because we know they're so active, we know they flare, how frequently they flare, what's the flare energy distribution of these stars, ultimately has pushed us into building our own small satellite in order to monitor, so that means stare. So our plan with SPARCS, and I'm going to go into this in more detail, our plan with SPARCS is to stare at M stars for a month, right? Something you would never be able to do with HST. Okay, so I'm going to go through each of these 3 systems: Galex, HST, and SPARCS with you. Okay, hopefully give you a comprehensive, as good a picture as we know on M-dwarf variability. So Galex is the Galaxy Evolution Explorer, and as the name suggests, was never intended to study low-mass stars. But in its giant field of view, there's of course lots of stars because M-dwarfs are everywhere, and so we can use the bandpass. These are the two NUV and FUV bandpasses to study the variability and evolution of low-mass stars. If someone has a question, I won't see your hand go up, so just shout. Okay, here's one of the papers led by an RU student, Brittany Miles, who's now a PhD student at UC Santa Cruz. And what she did here is she took about 300 M-stars that had multiple observations in Galex. So Galex was not a monitoring campaign, so it was only serendipitously where different parts of the field of the sky happened to be observed 3 or more times. And did a variability study, where here she's showing sigma over mu, so standard deviation over the mean, for stars in the near UV in red, the far UV in blue, as a function of spectral type. Essentially what you're seeing here is that in the near UV, the stars vary at lower amplitudes than in the far UV, and that the variability levels increase as you go to lower stellar masses or later spectral types. Okay? So now we can kind of figure this out. This was actually really helpful in designing the SPARCS photometric requirements, because now we knew, right, that we don't have to design an ultra-precise photometer because these things vary at many percent levels, right? So that's okay. So we're aiming for 1% photometric precision, and that's just fine for this kind
Are these
of
all main sequence stars?
yes, these are all main sequence stars. But onto some non-main sequence stars. Thank you. So here I'm showing you also from Galex, using Galex data, the evolution plot that we were able to make using a statistical sample of M stars. These are just early M's. Okay, so this is from M0 to about M3. And you can see the evolution now using stars of known age. And we know their age because they are members of nearby young moving groups. And that's a whole talk in and of itself of how much time we have spent, and many others have spent, trying to find low-mass stars of known age. Once you have that, right, we are now able to plot out the evolution here, right? And it's tracing the timescales that we care about, right? So we have disk dispersal and giant planet formation that happens up until about 10 million years. Then terrestrial planet formation between 10 and 50 million years, and the formation of the primordial atmosphere, which may or may not stick around to be the long-term atmosphere. Earth's second atmosphere is thought to have started between about, 50 to 500 million years. And if the secondary atmosphere survives, then maybe life will evolve. But at all these stages, we need to understand the ultraviolet. Okay. Now, here's the problem, right? So what I showed you up here was just the dots, and those were the median values of a sample of roughly 20 to 30 stars per dot. If you plot the entire range of the ultraviolet emission observed with Galex, it spans orders of magnitude at every age. Which means, which begs the question, is every M star the same? If you have an M star of a given age and a given mass, and probably then also, it must be also the same, now that I think about it, the same metallicity, because they formed together with all of the group members, its UV emission is not really predictable in a very clear way, at least not with large error bars. You've got the median, you do the median, you can do the inner quartile and all that. So you can do it. It's better than nothing, but it's still problematic. So that's just a caution. I think it's valuable. I mean, this makes me think how valuable it is to then look at the stars, not just statistically as we've done here, but also individually on the stars that have the planets we are most interested in. But what this also shows is what you might expect is that M stars do stay active for much longer, right, than the sun. Here I'm just showing you the solar activity evolution. Right, it starts tapering off after about 10 million years as the star spins down, but M stars stay active for much longer, right through those planet formation timescales that we talked about earlier, and then starts coming down. Okay? I think we kind of knew that. Now we have the real numbers for it. Here I'm showing you now the difference between the late M's and the early M's. Okay, so now we're talking about M0 to M3, and then or M0 to M3, and then M4 to M7, I think is what's in the sample. This is a paper led by another postdoc in my group, Adam Schneider. So you can find this online, but essentially it's saying that not only do early M's, like I showed you earlier, stay active for much longer, but the later M's stay active for even longer. The dots here are medians, and the inner quartiles are the error bars. So even though I am not so worried about M dwarfs as good habitable planet hosts, I know that the community thinks that could be problematic, and it could be. I don't know. I remain agnostic on that point. But I then sent my graduate student off to study K-stars because it's possible. There are arguments as to why K-stars are super habitable. Right? They're less active, the habitable zones are further out, they still have long main sequence lifetimes, longer than the sun. But there is an observational challenge for K-stars right now. Right now, our best bet to look for biosignatures is in the M dwarf regime, but in the future, we could be, if motivated enough, right, could be looking for habitable planets around K-stars. But this is what the exact same, so this is what she did, Tyler Ricciello was her name. This is what she did. She made a comparison, the same kind of evolutionary map with Galex of the late M's, the early M's, and the early K's at the habitable zones of their respective stars. And that's what it looks like. I don't know if lower UV means it's more habitable. Some people think that you need more UV for life to evolve. So whether it's good or bad, I kind of leave that up to you and your own biases. But this is just what the data show. Another thing we can do with all this beautiful Galex data is look at the ratios of the far UV to near UV, right? It's telling you what the slope is of the UV and the UV spectrum. And that's really important for photochemistry because you can create false positive biosignatures if you have a very high far UV to near UV ratio. And some earlier papers showed all this. And so here, this is the plot for both young stars and old stars as a function of stellar mass. Okay, and now I've confused you because now mass is going back in the traditional way, increasing in that direction. Sorry about that. But we've got the young stars, less than 50 million years old up here, and the old stars down here, and the sun is like way down here. So when you're thinking about photochemistry and you want to know what the ratio is, these are the data you want to use. Now, how can we use, as I said, the NUV and the far UV to predict the EUV flux? Remember, because the far UV and the NUV, the far UV and the near UV is really important for the photochemistry of those planets, but for the photoevaporation, you also need the EUV. So this is work led by Sarah Peacock. She's a PhD student for about another 2 weeks. She defends in 2 weeks at University of Arizona at LPL, the Lunar Planetary Lab. She is mentored by Travis Barman, a close collaborator of mine and a co-developer of the Phoenix models. And so they took it upon themselves to do this really challenging task. It's really not an easy thing to do. And that is to build chromospheres and transition regions onto the Phoenix models. And they're doing this by being empirically guided by the Galex data that we've already been collecting and the new HST spectra that we just finished one of our dwarf surveys on. And what you're seeing is the differences. Here I'm showing you 100 million, the yellow is the 100 million year old full spectrum of the star. This is of here it is, a 0.45 solar mass star. Then it's 650, the age of the Hyades is the blue, and an old M star is in pink. And you can just see the difference, right? That even what looks like a small difference in the near UV is a very big difference in the EUV. This is also numbers we need to know for the effort that we're doing. And Sarah has 2 papers already published and a third almost to be submitted. And the third one is quite fabulous in that it has all this evolutionary plots in there as well. But for the stellar physicists in the room, in addition to all the planet stuff, it's super fun to also look at the new information we're getting from these models of what might be the stellar upper atmosphere structure of these M stars, something that we also don't have, right? This is column mass and temperature. It's a bit more detailed probably than most of you want, but I find this really exciting because we really only knew this for the sun ahead of time. All right. So that's what we've been able to do with Galex, which is pretty nice for a given a mission that never intended to do any M-stars at all. So the HST's HAZMAT program, this stands for the Habitable Zones and M-dwarf Activity Across Time. It was a large program awarded 136 orbits to do a very similar experiment as we've done before with Galex, but now with spectroscopy, because really we need the spectra to get individual lines and line ratios and fit the models better and so on. There are lots of reasons why we needed to do that. And we used 3 ages. We took Tuck-Hor, the Tuck-Hor young moving group, it's 45 million years old, the Hyades, and the field sample. So we took the M-stars that we know and love in these age bins, and we observed in the far UV and near UV. And again, the blue here is the Phoenix model of just the photosphere, and we're trying to map out all the rest. So I can show you some preliminary results. We so far have 1 paper published on this sample, with more coming up, because it's a pretty big and interesting set of data. But even in this 1 paper, led by Park Lloyd, we see lots of fun flares. We have a total of 10 hours, not on a single star, but on 8 45 million year old early M's. Okay, we see a whole series of fun flares and so on, including this one giant superflare. It's called the Haz flare. And you can see it lasted for about 200 seconds, and it increased by a factor of 200. And if you work out the statistics of this, it turns out that this happens every day on a young early M.
What flux is that? What are you measuring? Is that a
This
line?
is the cumulative FUV bandpass that we observe. So if you add up all the FUV photons, so this is the FUV flare. Now spectroscopically, so to answer your question, or I know this is kind of what you want to see, which is the flare and the spectrum. So the quiescent is shown here in blue, and the impulsive flare is in orange. You can just see that the emission lines just completely blow up, right? So that's kind of fun and cool. But it's not just the emission lines. We also see the continuum region. It's not really a continuum, but the continuum region in between the lines also blow up. And you can fit this. This is not a straight line. You can fit this with a black body curve, which is a standard thing that people do with optical flare analyses. Where I'm showing you now. Here we have the quiescent flare. I've just zoomed out in wavelength. That's all I've done here. Here's the quiescent flare, the quiescent state of the star and the flare state of the star. Now also with the 15,000 Kelvin black body curve. There has been Cynthia Frying also published another flare with HST data with a best fit 40,000 Kelvin black body. And this is the typical 9,000 Kelvin one people typically use. So the question here is, how much energy is really coming out in these flares? Right? Like, I don't think we know. I mean, are we really, do we know? We have a bunch of other flares for which we are not able to fit. There's not enough signal to noise in the continuum there to know if there's really a black body associated with it or not, right? Are the optical flares that Kepler detected or TESS just the black body component of these flares that we're detecting in UV? And therefore, what is the UV lines really doing? And are we missing a whole bunch of energy there? I don't know. Maybe there's people in the room here who know the answer to this, and if you do, please tell me. I'm very curious about that, as we all should be. So, so this is a flare frequency distribution from this paper, where we compare, so here we have flare energy just in the far UV, right? Again, we're just trying to compare apples to apples. We're not trying to compare, measure the full UV and the full flare energy, because that in itself has some concerns and trouble and uncertainty. And what you see here, we've compared it to the old stars from the Mussels program here, and to the young stars that we have. And it is true, which we already knew going into this, right, that young stars flare more frequently and with more energy, but now we know that roughly it's 100 to 1,000 times more. So that's good. But what's happening down here? So this point here is the Haz flare, right, that constrains the end of this curve. Now the Haz flare comes from 10 hours of HST data. And even if our entire program, the whole hazmat program, is about a week of HST time. So what about the stronger flares that don't happen every week? Maybe they happen once a month, right? We want to know kind of what's happening in this range here. And that requires monitoring because you need to find the rarer, stronger flares.
Excuse me, what was the power index or indices for those?
I don't know offhand.
No worries.
Okay. So how can we efficiently monitor the M stars in the UV? So what we really want, so kind of a dream, right, is to have Kepler or TESS in the UV, right? That would be amazing. So you get something like this, and this is what we're aiming for. We're aiming for something that would get rotational modulation of these low mass stars and rotational modulation and the flares, right? That's what we really want. This is a Kepler light curve, of course, but this is kind of what I dream about in the UV. In order to do that, we conceived of SPARCS, the Star Planet Activity Research CubeSat. SPARCS is a NASA-funded mission through the APRA program, the Astrophysics Research and Analysis Program. It is led by myself at ASU, and JPL, and University of Arizona, University of Washington, Lowell Observatory, and Surrey. For those of you who have never seen or held a CubeSat, it's small, so small that I could have brought it with me on the plane without checking bags, but then I figured I could just show you a picture. So SPARCS is a 6U. It's one of these, and a U is 1 unit. 1 unit defined as a 10 by 10 by 10 centimeter cube, right? And so we're 6U. And it's about, I walked around my house looking for something that is about as close to a 60 as I can find, and it's the family size Cheerios box. Right? The family size, which is significantly bigger than the regular, so please don't. Please don't think it's any smaller than this.
Is that 1U, the Cheerios, or
No,
is that 6Us?
That's a 6U. This is a 1U. A 1U is the 10 centimeters version.
Okay.
But we're going to do science with a 6U. We can do it. So here's a quick fact sheet of SPARCS. So it's a 6U with a 9 centimeter telescope with a 0.7 degree field of view, which is good because there's going to be a lot of other targets in there that people could do other science with. Like maybe galaxy people now want to use an M-dwarf mission to do galaxy science, right? That's possible. It will have active pointing. It will have a UV camera. It's going to be a 2-channel camera in the far UV and near UV separated by a dichroic. As I said, these things are flaring at such high levels. This is not an ultra-precise photometer. 1% is fine. We're currently funded for a 1-year mission, but if it all works, then presumably we'll be allowed to continue monitoring it. So this is kind of what it looks like. We've actually have we've now changed the design since this picture to look more like, let's go back up. Oh, I'll show you. Anyway, our solar panels are now in a different place, but you don't care about that. I care about that because we worked really hard on figuring out where to put the solar panels, but okay. SPARCS targets. So it's the same idea of evolution. I'm a little bit obsessed with the evolution of stars because knowing what happens early on is so important for the planet question. And so we have designed, very similar to the hazmat program, a sample of young stars, intermediate stars, and old stars. And if we have an old star that is bright enough with a transiting planet, we'll certainly look at it as well. But it is not specifically a transiting planet mission. It's not quite the dream TESS and UV that I have. It's just it's a stepping stone to that. Our sample, our target list is this is what NASA likes to call the undiscovered country plot, for those of you who do mission work with NASA, right, where you show kind of what's been done and what your mission is going to do, right? So this is the fraction of stellar rotation for our targets that have ever been observed in the UV. And it's only in blue, and then we're going to, do a lot more UV observations, because UV observations are pretty scarce and hard. And this winner here that has 10 hours of observations is 80 Leo, in case you're curious. Very famous one. So SPARCS is relatively cheap. This is to scale of Galex at about $200 million, and SPARCS, which should be about 6, million mission. And so you're probably thinking, what makes you think you can do this? Because I don't know any better, you know. This is how you start new things, right? You're like, I don't know if it can happen. But what makes us think we can do this, right? And there's papers, there's SPIE papers that detail all the technical engineering that you might be interested. But the first thing is you get a really interdisciplinary and creative team that likes each other, because you gotta hang out together a lot. So pick your teams carefully, and we do have a fabulous team. This is them, and they all do different things, and they contribute in different ways in science and technology and operations and so on. Hopefully you'll recognize some of these names. But another reason why this can be done, we think, in a small satellite is because of these new fancy detectors that are developed at JPL. These are delta dope detectors. They are designed to have about 7 times the quantum efficiency of the detectors that were flown in Galex. So we're making up for this small aperture in detector efficiency. Not all the way, we're not going to be quite as sensitive as Galex, but pretty well. And our bandpasses that we've designed specifically to measure emission features, we call it SFUV for SPARCS FUV and SPARCS NUV, and they're designed to catch features in the M dwarf spectrum that we're interested in. Right, so we have some transition region features and some chromospheric region features.
How is the sensitivity in the? Can you back up a slide? In the quantum efficiency in the shortest wavelength.
Oh, the shortest wavelength. It's comparable. I just didn't put it on here because it was going to be, but it's comparable with RUV. If anyone, I have comments on red leak if anyone is interested in, because it's a big challenge for M stars in the UV, as I said earlier, right? You have 1 million red photons to 1 blue photon. If you don't, if this curve is not like 5 orders of magnitude down here, you're in trouble. So we spent a lot of time thinking about red leak. Also something I didn't know ahead of time. Okay, so let's put SPARCS into scientific context. So we fly SPARCS. We measure the UV light curves. So we're looking for the rotational modulation and the flaring over top of that. Then we use those data to build these new upper atmosphere models that Travis Barman and Sarah Peacock are working so hard on. And then we will have really much more accurate UV spectroscopy that we can then apply to planet photochemistry, photochemical models, and then take those models that are now exposed to more accurate UV fluxes, right, and compare those to those that will be observed with JWST or any other big mission that you might be thinking about. And then if you're interested in habitable zone planets and detecting biosignatures, this whole stream of thought, this is kind of how I envision the value of not just SPARCS, but in fact all UV observations when we want to talk about planetary atmospheres. So, where are we now? So NASA missions go by phases. And so pre-phase A is kind of when you're brainstorming, you're doing feasibility studies, and we did a TMEX at JPL to see if it was even engineering-wise feasible. Do you guys know what a TMEX is? Yes, some of you do. TMEX is like a hackathon for your crazy idea. Okay, so you go to JPL and you stand up there and I give a talk, and there's 20 engineers, and then they go to work for 2 days and see if it's possible to even build and do anything that we said. It's totally crazy and fun. So, yeah, but it's great. It's a great thing to do, and they have a really great system on how to do it fast. So right now we're kind of here in the phase A. We've done all this. We were funded up around here. We did a preliminary design review. We've paid for our telescope and our camera. They're arriving at ASU in March of 2020. And hopefully we'll have all the pieces in place at ASU, and we're going to do all the testing, integration and testing at ASU. That's our plan right now. And we're aiming for a launch in early 2022. Part of that, we can't say for sure when, is because when you are going up as a CubeSat, you're essentially hitchhiking a ride, and you just don't have enough choice of where you're going. So just like with hitchhiking, you don't know what direction or what orbit you're going to get into. So we're aiming for a sun-synchronous orbit, and we're willing to wait a few months until we get the orbit that we really want. So when that happens, I cannot say for sure. This here is SPARCS in programmatic context. This is a slide that Thomas Zurbuchen showed last year at a SmallSat conference. And what you're seeing here is all the NASA investment in small satellites, including CubeSats. And you can see that there's some going to the moon, including LunaMap, which my next door neighbor, Craig Hargrove, PIs up at ESU. We have a bunch that do the Earth, look at the Earth. Marco, you've probably heard about, went past Mars already. A bunch of sun observatories. And you can see the astrophysics up here is kind of like the last investment NASA is doing for, in small sat science, I think, because of this idea that bigger is always better in our field, right? But the time domain is lost. However, NASA did not fund the first astrophysics CubeSat. JPL internally funded one called Asteria that was led by Sarah Seeger. And she was the PI, and the project scientist is Mary Knapp, who's also now at MIT. This is actual footage of Asteria being spat out of the International Space Station. Can you imagine spending years and years building something, and then there it goes by itself? Good luck. You know, I don't know. It's very. I'm hoping not for an ISS orbit, so I'm hoping I never see a video of SPARCS like this because I don't want to be on an ISS orbit. But still, it's quite remarkable. And then, so they do have now, Asteria is still working. It's been up there for a couple of years, I guess almost 2 years now, and it's still functioning. It's amazing. And it's measured the first CubeSat detected transit, and that's something from Mary Knapp's upcoming paper, 55 Cancri. Now, in general, exoplanet science is really quite well suited for small satellites, right? Because we have lots of targets. They're relatively bright. They're all over the sky, right? A lot of the phenomena we're interested in are time domain kind of things, right? And so small satellites are quite perfect for that. And here are just 3 examples of concept studies that NASA funded last year. I don't know if these are all going to become small satellites' actual missions, but they've been funded to continue with their ideas. Bruce McIntosh leads the MDOT project, and that one is to test starshade technology. The MASS, micro-arcsecond small satellite, is to find Earth mass planets around Alpha Centauri in a small satellite. And this one, you know, from Scott Wolk, your collaborator, he won a small sat concept study to do transits of giant planets in the X-ray. So there's just a lot to do. And there's much more room, right? So this is all, let's see. So this is from a paper that I wrote last year, rather optimistically titled, I should say, On the Verge of an Astronomy CubeSat Revolution. I'm not sure I'm wrong yet. Time will tell if I'm right or wrong about that. I don't know. But the AAS has 2 astrophysics CubeSat workshops going on this January. So if you're interested in that, you can let me know. Anyway, so these are the ones that NASA is funding. This one is up already. HaloSat is an X-ray experiment out of Iowa that's already up. No one is funding radio swarms. I left this in here because I'm very interested, if you were at my earlier talk, in exoplanetary magnetic fields, and I really think this is the way to go in that direction. So if you have any ideas that if there's something that existing missions are not quite doing what you want, the experiment that you want, I encourage you to think about this because I think it's only growing. NASA is starting to fund more of these. We were kind of in the first wave of them trying to figure out how to do small sats, and now I think they're realizing they're more expensive than we originally had hoped CubeSats would be, but still much, much cheaper than everything else that they do. So anyway, keep your thinking hats on. So I just want to leave this up as a final slide that I think, not just for SPARCS, but for both small sats and big sats, a word I've never used before until today. I think that the UV context is really critical in exoplanet science, so keep that in mind. Thank you.
Questions for Jenny?
One technical one. Are your solar panels steerable, or are they fixed?
No, fixed.
So you're limited by the orbit to a stripe of sky, but you can point within that within
No,
the
you can
asteroid?
angle it. You can angle them. Then you just can't, you can angle the whole mission to point, and then you just lose your solar efficiency.
Okay, so
Right.
yeah.
So no, we're not limited to just the anti-solar direction.
No, not the anti, but
Okay.
wherever your solar panels, because you have a limited angle range,
Yes.
so that you can do your solar panels at. So you,
Yeah. It's true. There is a limit. It's not the whole sky.
Yeah.
But it's not so limited.
Go ahead. I'll go next.
So you mentioned that the emission had very big error bars in the.
It wasn't error bars.
Well, not error, but in the
range, yeah.
distribution.
Mhm.
So I was wondering, is that distribution in any way? Is it like uniform, or is it bimodal, or and do you have
It's
rotation
not
periods for
bimodal. It's not bimodal, but it's also not Gaussian. Right. So that's why we report inner quartiles.
that? Do you have rotation periods for it?
We have rotation periods for a lot of them, but and no student of mine yet has plotted up the rotation periods as a function of emission.
And a small other question. You said you're gonna use all this information to put it into the atmospheric models.
Mhm.
Do you think the atmospheric models are there yet to take all this very detailed information? How much difference do you think it will make, and how much progress do you need in the atmospheric models in order to make something
How much what, sorry, do you need?
improvement using these
In the
models?
stellar models, you mean, or the planetary?
No, the planetary atmosphere.
So, okay, the planetary atmosphere models do really need these because the results, as I showed, are significantly different. And those do not yet, we have one person, Matt Tilley, who is working on the effects of flares, individual flares on the atmosphere of a planet. And so he has a very nice paper in 2019, I think earlier this year, where he has one flare affecting a planet, and you can see the effect of ozones, for instance, and the recovery rate. Now he's working on what happens when it's multiple flares, because from the HAZMAT program you can see that the large flares happen every day on the young stars. We don't know what the statistics are for those kinds of flares on old stars yet, but the time scale is much shorter than the recovery time of the planet atmosphere. So we still have to work out. So they need to work out these models, and they're starting to use more realistic variability data for the planet models. But it's a big question.
You put up a slide of your chromospheric models that I believe you constructed from the Galex data predicting the far UV.
Yep.
You could also use, optical and near-infrared spectra and figure out what's happening in the chromosphere. In other words, if you look at the H-alpha lines and the calcium lines and the near-infrared helium
Yes.
lines, you could do that. Have you tried doing that to see if it matches?
Sarah Peacock, who's leading this work, I think, well, she's certainly trying to fit the Lyman alpha observations, because some of them have Lyman alpha observations from HST. And I think she's working on H-alpha. I don't think she's gone redward of H-alpha, but she is
Because
trying with
you can
H-alpha.
probe it by using
Yeah.
optical and near-infrared lines.
True, but it
See
depends on the formation temperature. So yes, you could do with H-alpha and get the chromospheric temperature at which H-alpha is 4.
Yeah, but you can get up pretty high with, near-infrared, you go up 20,000, 25,000 degrees.
With what? The heat? Which line?
With
helium?
10-830, yeah.
Yeah, that's an interesting point. I actually don't know of any observations of these particular stars at the
Carmenes has lots.
has lots.
We have
I don't know
lots.
what these
There are
stars.
lots, yeah.
No. We're looking right. Statistically, we could just use archived ones.
But we
That's
have
right.
lots of M stars.
Yes.
They're right
Okay.
there.
I'll suggest that to her. That's a good point.
Yeah.
So nice stuff, Jenny. So
Okay.
the question that you asked or put out there about the correlation of heat layers with the black body
Mm-hmm.
and the optical is important. And I wonder if you have plans for simultaneous observations, at least of some of those stars that's hard to try to observe from the ground in the optical.
Right. So excellent. Thank you for asking. We do have plans for when SPARCS is launched to have our entire schedule published on our website, so that people, we and others who have access to telescopes, spectroscopy, photometry, can go and monitor simultaneously. That would be very interesting. That's part of our plan, for sure. Yeah.
What limits the size of that aperture to 9 centimeters? Is it just a single unit or?
Yeah, because it has to fit into 1U when you consider all the other stuff that has to go into the box. You're limited. Although I will say that Qt, which is another 6U, has an interesting design because they're doing a near UV low resolution spectrograph. They have their telescope pointing off one of the broad sides. The scattered light analysis for our photometry wouldn't work for
Your aperture
us.
is off the narrow side.
Off the narrow side, but theirs is off the wide side, but they're doing spectroscopy, and it just didn't work for us. We also looked into that possible configuration. And then there are people who are also working on deployable mirrors. If you can, I don't think you're doing the optical yet, but at longer wavelengths perhaps too. People are working on tech development for that. For now, ours is just limited by that 1U side.
So you mentioned that you want to observe like on a time scale of a month, roughly. What's the cadence of the data?
It's a good question. So here's our plan. What was your question? Our plan is to start out for about 1 minute observations for the brightest sources, 10 minutes for the really faint sources. So your next question would be, but you're going to miss the big flares. That's true, but we also are writing, we're not going to miss them, well, we're going to try not to miss them, because into our software, we're going to do some onboard dynamic exposure times. So as soon as a flare is detected, we decrease the exposure times to much shorter, and our requirement is that we can expose 1 second exposures at minimum.
How bright or fine will be the targets?
How bright they are? I can tell you in Galex magnitudes. Someone asked me today about what the Z magnitude of it was. I looked it up. In Galex magnitudes, the faintest stars would be about 18 in Galex magnitudes. And to give you a sense, AU-MIC is our brightest source. It's a 10 parsec active UV, famous kind of M star that we know and love. That is 12 and a half or 13. I think it's 13 in Galex MUV. It's magnitude. So between 13 and 18.
What are the rotation periods going to be of these stars?
Yeah, so the youngest ones rotate very quickly, like 4 days, 5 days, and so on. And the oldest ones are about 30 days, 30, 60 days. The ones that are 60 days, I don't know if we would actually monitor the entire way, but it also depends what, I mean, this is one of the beauties of having a kind of a dynamic observing program is you can observe for 2 weeks, and if it's not doing anything interesting, you can want something else too. So we can see, or, you know, or we just stick it out, do the whole thing, and wait for that one flare that might be a 1 and 2 month kind of flare. So those strategies. The hope is to get one full rotation period at least for every star.
Okay, last question. Well, let's thank Jenny.
Congratulations, you've done very well.
Oh, thank you.
I haven't seen you for a long time. I see you've really built a really nice
Yes.
for your observations of M stars, is something 500 parsecs a little too far?
Yes.